Okay, so let's talk about gravitation. Some basic things about gravitation. There's, I'm going to be going through this kind of alongside the book, so you kind of see which chapters you really need to be looking at, and just trying to summarize the main ideas in each chapter. So, first of all, if you look at the first chapter, you'll find that in most of the other chapters, they don't really talk about the history as much as they do when we talk about gravity or astronomy. Because when you look at the history of science, the birthplace of science really is in astronomy. In no other field were they as dependent on observation. Okay, in most other fields, at that time, when you look at medicine at the time, like they were doing lobotomies and blood drainings and things like that to like get the bad stuff out of you, right? And that if you got sick, it was a curse from the gods, that kind of thing, right? We're talking about 1500s, right? So, but in astronomy, where when we change from the Earth-centric kind of model of the universe, that the Earth's at the center, and it's actually kind of crazy the different kind of models that people have come up with for the model of the universe. It was Ptolemy from where I can't remember which region he was from, but his model was basically this: you have the Earth, and that surrounding the Earth was like this veil. It's like a sheet, a sphere, where the stars were just like kind of put around on this sheet that like surrounded the Earth, and that and the planets and everything rotated like on that sheet, and that sheet would just like spin, and that if you could poke through that hole, then that's like where the gods are and stuff like that, the heavens. And it wasn't until Copernicus that was like, well, that model doesn't really describe the motion of some of the observations that he had made with the different planets. And then we get to Galileo. Galileo is the first person to make a telescope, right? Creates a telescope, cuts, kind of makes his own lenses, makes his own telescope from scratch, and starts recording information, right? Actually, was it? Yeah, I'm pretty sure it was Galileo. I can't remember if there was someone before him, but I'm pretty sure it was Galileo. Maybe. Yeah, I'm a little shaky. Actually, I think. Yeah, I'm a little shaky on that part with the lenses. There's this other guy, Tycho Ray, and either way, they were more dependent on taking data and trying to figure it out from the data instead of just assigning phenomenon to the work of gods and stuff like that, right? And that was very popular at the time. So we really do credit kind of the birth of science in terms of looking at things objectively from astronomy. Another thing that kind of was important was once through astronomy and understanding that the sun was at the center. Well, first we thought the sun was at the center of the universe, and then further observation showed that there were other kind of galaxies and solar systems. Well, probably galaxies, where it would appear that our own solar system was not any more special than any other solar system or galaxy. It kind of got us away from thinking that the Earth was this super special place where God believed that Earth was like the most important and everything else was whatever. It made our understanding of the universe and phenomenon much more objective instead of human-centric or subjective. So that was also a very big jump. And so I don't think this history really does any justice to the amount of history that goes on here in between like the 1570s to the 1640s or so. That's really like when Galileo was doing a lot of his stuff. But yeah, there's a lot of history here. Second of all, as we go through these laws and stuff, there's a lot of simplifications that we're doing here. First, we're going to be, okay, let's go through some of these laws. All right. So first, when you look at an orbit, okay, when an object is under the influence, when you have gravity, right, two objects pull on each other, and because they're already moving, they kind of swing past each other, and the resulting behavior or motion is an ellipse. Okay, so that is Kepler's first law. Kepler's first law says planets move in elliptical orbits with the sun at one focus. This is a simplification because obviously the sun is not the focus of every single orbit in the universe. What it is saying is that planets tend to orbit around a focus. If their path is an ellipse, there is a focal point that they tend to orbit around, and generally that's actually going to be the center of mass. Because the sun is so much more massive than the Earth, then the sun tends to inhabit that spot, the focus. If you look at binary stars or other really massive objects in space that are orbiting around each other, they both move. Okay, the two stars will orbit around each other, but they'll both move, right? And they'll both orbit around a seemingly common spot, which is generally their center of mass. But that center of mass is the focal point of their orbit, right? Okay, so when you look at an orbit, there's a couple words that aren't necessarily going to be on the AP exam, but if you are interested in any sort of astronomy or aerospace engineering and stuff like that, you need to know these terms. So, for example, if watching Hidden Figures inspires you at all, there's two common points or important points of an orbit is the closest approach and the furthest approach. They're the two ends of your ellipse that really do define your orbit. And it depends on whether you talk about the sun or the Earth or just a general orbit. It's interesting because a lot of these words really just come from the history of the development of our science in, I suppose, aerospace engineering or astronomy. So if it is the sun that you're talking about, the closest approach, we call it the perihelion. Heli is the root word for sun. It's like named after the god, right? What was his name? Helios. Yeah. So peri is the root for closest approach, and then apohelion is the furthest approach or the furthest distance. If you're talking about the Earth, you have the perigee. Okay, so you think of geosynchronous orbits or geology. That G is the kind of root word for Earth. So perigee is close to the Earth. Apogee is far from the Earth. And then if you're talking about a general, any kind of orbit, periapsis is your closest approach, and then the apsis is the furthest approach. Okay. So if you ever go into astronomy or study orbits, those terms come up a lot. All right. So Kepler's second law, and these are all in your book. I literally copied them directly from here. So if you want to copy them, that's up to you. But when you're looking at Kepler's three laws, these are laws in the sense that they are observations Kepler made, and they hold true. Now, these are not mathematical, but there are mathematical representations of each one of these. And so, there are, when we say they're laws, there are equations that go with them. We just don't have them here. Okay, so second law, a line drawn between the sun and a planet sweeps out equal areas in equal time. So if you kind of look at this diagram, this is kind of what it's representing. As you get closer, right, because your distance is shorter, right, to sweep out as much area as this sweeps out, you kind of need to turn at a faster angle. Basically, it just means that when you get closer to your focus, as you approach your periapsis, you go faster, right? So comets, asteroids, whatever, when they're slow far away, and then they go slow, and then fast, slow and fast. That is essentially what Kepler's second law says. And lastly, the third law, in the book it says the square of a planet's orbital period is proportional to the cube of the semi-major axis. Now, I think that's a mouthful, and this is a lot easier to remember. T squared is proportional to a cubed. When we talk about the semi-major axis, if you remember how ellipses look, the semi-major axis is not the full width, right? Kind of like your radius. The semi-major axis is just that. It's the from this center out. Okay. So one of the simplifications that we're going to see a lot in this unit and for the AP exam is that you will probably not really deal with any actually elliptical orbits unless it's a very conceptual question. Any of the math related to elliptical orbits is very complicated, and instead we deal with circular orbits. And it simplifies everything by a lot. Once you have circular orbits, your semi-major axis becomes your radius, right? The way to think about an ellipse, a circle is an ellipse, but an ellipse is not always a circle. A circle is a special case of an ellipse when your two focus are on top of each other, right? When your semi-major axis, when your two focus are on top of each other, your eccentricity is 1 or 0. I think it's 1. And then your radius becomes your semi-major axis. Is it 0 or 1? I don't remember. It's one of those extremes, your eccentricity, whatever that measures how elliptic it is. Okay, anyway. Okay, so those are Kepler's 3 laws, right? They describe how things move in space. Any questions about those observations, thoughts? Okay. Okay, so the next law that is extremely important is Newton's law of gravitation. This describes the force that objects apply on each other that ends up resulting in all this motion. Which is actually another point I brought up in third period is that, again, the history of astronomy is so important because it was really under the request of analyzing the data that Galileo had got that kind of led to Newton trying to figure out why his data was the way it was, which then he was like, oh, well, let me invent calculus to figure it out. And, so he does that, and he figures out his laws of motion, he figures out his law of gravitation under the impetus to figure out orbits and this motion in space, right? So it's interesting to think, if we didn't have this history of trying to figure out how things move in space, if Isaac Newton really would have done all the stuff that he did. Or he maybe would have done it later, and then we wouldn't be crediting him for calculus, we'd be crediting Leibniz for it, whatever. So let's look at this law. F, the force of gravity, and in the book it looks slightly different. Okay, in the book it looks slightly different. In the book it looks like this. I'll put them on top of each other as best I can. Okay, so here is how it is in your equation sheet for the AP exam. This is what it looks like in the book. This in the book gives you the magnitude, but it does not give you the direction. Okay, this is a more complete definition of the force of gravity because gravity is a force, right? and that means it's a vector. So let's break it down just a little bit. First thing you need to know about this law is that, remember when we talked about Newton's third law, we said that, well, if you weigh like 130 pounds, the Earth is pulling down on you with 130 pounds, but that also means you're pulling up on the Earth with 130 pounds. That is the action-reaction pair, right? Which means that you'll never have gravity exist like a planet pulls on an object and that's it. In order for an object to pull on another object, it itself must be pulled, which means that gravity is always a mutual attraction. It's not just the Earth's gravity is pulling on something, it's their gravity pulling each other. Does that make sense? We have different models to kind of separate them, and that's where the field model really comes in and helps. But in other words, you as far as the force goes, you can't have one without the other. You can't have this pull on that without that pulling on this. Okay? They come in pairs. It is always a force of attraction, and that's really where this negative comes in. Okay, that's where this negative comes in. If you're looking at this as the force of object, I know that's kind of hard to see, so I'll zoom in on this a lot. This is the force of object 1 on object 2. That means that this is a force measured from the perspective of 1. So I'm this mass, I'm sitting here, I see this other object a distance r away. How much force am I going to pull on it? It's by this much. And it is in the opposite direction of my r vector. Okay. That part can be a little weird in terms of what I mean by the opposite of the r vector. Think of it this way. If I'm on this planet or this object, and I'm measuring how far this object is, right? I would set my coordinate system on here, and I would measure it to be like some distance out and some distance up, right? So my vector r points this way. It points this way. R points from here to here. Then therefore, the force of gravity is always opposite of that. It points the other way. Okay, so that's how you mathematically represent it to always be an attractive force, because it's always opposite of where I'm pointing. So if I'm pointing to Oliver, his attraction is the other direction. Pointing to Angelina, it's the other way, right? If R is that way, force of gravity is the other way. The other thing to note that this is a unit vector. Okay, the unit vector, just a reminder, is a mathematical way of representing a direction and only a direction. So for example, if I have an object that is 45 degrees from me, if I only want to indicate the direction, I might say that the unit vector is root 2 over 2 this way in the I direction, and root 2 over 2 up, which gives me 45 degrees, but the length of this vector is 1. That's really useful because now all I do is I multiply that unit vector, which gives me my direction, by a scale, how I'm going to scale it, the magnitude of it, which is just this, right? So this number times 1 is just, that makes the length, whatever I want. Does that make sense? How we're building our vector here using unit vectors? I don't know if you remember how unit vectors from pre-calc. Did you guys do unit vectors pre-calc, right? So unit vector just helps us figure out what direction, and then we just scale the length of it with its coefficient, with its magnitude. Okay. So let's look at the equation itself in a little more detail. So now we talk about the direction and so sort of. This big G is the universal gravitation constant. So on Earth we had little g. We said it was 9.8. That number actually comes from this number, right? Little g is actually just the combination of the fact that we're on Earth. So we combine the mass of the Earth with big G and divide by the distance from the center of the Earth, or the radius of the Earth, squared. Right? So little g is just coming from like this. That's little g. So this is the more general form of gravitation. So when we say your weight is equal to mg, that is specifically for the surface of the Earth, and this is a more general case. So this constant is really small. It's really small, 10 to the negative 11. So that's why you end up having really, really massive things to pull on other things with actually a pretty small amount of force, right? And that's why things in the universe just take so much time to happen. It takes a very long time for things to come together, for things to happen. Okay, so notice the units on G. It is whatever units you would need to go from a mass squared on top divided by a distance squared on the bottom to convert it to newtons. So you see that the kilograms squared is on the denominator to cancel with the kilogram squared that you'll get on the top, and so on and so forth. Sometimes I forget what those units are, and you'll see it in different contexts. In this context, it's really easy to figure out what G is supposed to be, because you need to go from this and turn it into newtons. So if you ever forget what the units ought to be, I would look back at this equation and be like, okay, what were the units supposed to be? And then kind of backtrack it. So when you look at this equation, again, notice that you have two masses. Okay, it really reflects the fact that it's a mutual attraction. It's not just the mass of one object, it's the mass of both objects. So my mass matters in what force I experience from Earth, just as much as the mass of the Earth matters. It's also inverse square. Okay, so that means that force of gravity drops off really fast. Here's a graph of it. Right, it's an inverse square pattern. So when I double my distance, I actually get a quarter of the force. So if I triple my distance, I get 1/9 the force. Right, it drops off really fast. Yeah. Okay. Any questions about Newton's law of gravitation? Yeah.
What is the universal gravitational constant really representing? Well, to me, it's just a number right now.
Yes. So good. That's actually a really good question. In physics and in engineering, in science in general, a lot of times we do experiments to find the relationships between variables. So all that stuff I told you guys about doing the best fit line to find the best kind of equation, looking for proportionalities. So we say that, like in Newton's second law, F equals ma, we would say that the force is directly proportional to the acceleration, or acceleration is directly proportional to force. So if I double one, I double the other. That's really useful for figuring out how things change, right? Or another example is okay, just kidding. Maybe not the best example, but they're just proportions. They don't give us the actual value, right? They don't give us the actual value. So a lot of times, what we do is we will do experiments where we change one thing, control the experiment for all variables except for one other thing. As we change one, we see how the other changes, right? So that we get the proportion, but then we take a bunch of data and come up with a constant, some number that relates them the actual values. So all this number is doing is it's relating the actual values, even though we know that it's linear with mass and it's inverse square with distance. But at the end of the day, we need a way to actually get what the actual value is. That's what all this number does. Sometimes you can theoretically come up with those constants. Sometimes you cannot. So for example, there is a constant for magnetism. It's called the permeability of free space. It is 4 pi times 10 to the negative 7. That's oddly specific, but it is exactly 4 pi. And pi is a irrational number, right? So it's not a measured number, that is a theoretical outcome, right? 4 pi times 10 to the negative 7. Whereas something like this is experimentally determined. You can do an experiment where if you're very careful, you take, well, they actually have an example of how they did this. You take a bar with 2 masses, you put it on a torsional spring. So in other words, as it twists, just like we use spring scales to measure a force, here we're measuring a twist to determine a force. But this is very, 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 very sensitive. And you put them next to 2 massive objects and you wait for like a long time without disturbing them. And you see how much it moves. And then you can kind of figure out from there, you get, so in other words, how can you solve for G? How can you figure out what this constant is? You need a way to figure out know M ahead of time, know R ahead of time, and measure F, so then you can get G, right? And so that's what that experiment does. Yeah. This is, I believe this is like, this is experimentally determined. Just like how we count how long a second is. I don't know if you guys know, like how the scientific community has determined that the length of a second is based on like the radioactive decay of some element. I can't remember what, but it's like saved, is cesium. It's like stored in France, and it's just in a vault. And everyone has agreed, okay, based on the half-life of cesium, because you can measure how much cesium you lose, and then you determine what will count as a second for that. So it's experimentally determined. All right. Let me see. Moving on. Okay. On this page, I'm kind of going through the book, trying to summarize or explain some of the concepts here. So as you're reading it, it's not like super. I would say as we go from this chapter on, we're gonna start getting into in the realm of very intangible things, and a lot of times that makes it really difficult to understand. Like parabolic trajectories, super easy, right? You throw something, you can see it, you can do it. You take a pen, you can throw it. But like gravity, you can't see gravity, you just experience gravity. It's really hard to understand it sometimes. This principle is really interesting. What it's saying is that when we look at Newton's second law, F equals ma, we say, okay, I push on something, it accelerates at a certain rate, and how quickly it can accelerate depends on its mass. This thing we call mass. And now, in this equation, I give you G, M1, M2, and without even blinking, I'm sure you're all assuming that's the same mass. That mass is this measure of how much stuff or material something has. But it's actually really interesting you think about the assumptions we're making here. When we push on something and it resists motion, that resistance is an inertial mass. It is how it resists motion. There's nothing about that has anything to do with gravity or an attraction between one object and another. When you talk about this law, the force that 2 objects have that attract on each other based on some